Alright, so the title of the talk is Exploring Starry Realms in the Milky Way using Gaia. And Starry Realms just means we are looking at stars in the Milky Way, that is our galaxy, and Gaia is the satellite that we'll be talking about. Alright, so if you need to like run the code yourself, you can just go to this binder link. So it is bit.ly/Gaia-notebook. If you want to like run the code yourself, you can do that. But otherwise it would be fine. There is not a lot of code. So first of all, how many of you are known to astronomy? Like how many of you know astronomy, a bit about astronomy? Alright. How many of you know just a bit about Python and like counting two libraries, pandas and matplotlib? Just basics. Alright, great. And how many of you know the basics of SQL, like writing select star from where? Great. Almost everyone knows these three things. That would make the talk slightly faster. So first of all, astronomy, not a lot of hands were raised. So astronomy is the study of celestial objects and phenomena. So whenever we look up at the sky, we see stars, we see planets. We hopefully also see exoplanets, which are planets around stars other than sun. And there are exomoons. There are moons that are present around these exoplanets and so on. What I do at ASIAA is working on finding these exoplanets, but this is all like the type of stuff that we do. And how do we do astronomy? There are like astronomy is kind of the oldest science that we have known, because people always looked up at the sky and drew things. So those were the earliest records of astronomy, and they also did some mathematical calculations. They drew calendars that we even know of today. But nowadays we have data. We take data from telescopes and we process it. And there are two different fields of astronomy. One is observational astronomy, where we take data, we look up at the sky and take data, and we process it, and we draw inferences based on physics, mathematics and chemistry. And the other branch is the computational branch, which basically uses this physics, maths and chemistry to simulate and to create computer simulations and analytics, so that we can understand the phenomena that might be happening there. So observation is a kind of middle ground where we confirm our theories. So this is an image of the moon that was drawn in earlier ages. So people were just drawing the moon and phases of the moon. And nowadays we have telescopes. Telescopes are just instruments that we look up with at the sky. And the first ones were made by Galileo, if you have heard the name. So he was just making a visible light telescope, so that it can just magnify what we were seeing. And it's an interesting story. So he said that I'll be making this for warships that are coming onto our land. But he was actually not making it for that. He was making it to look up at the sky and the stars. And nowadays we have telescopes that range from all ranges of electromagnetic spectrum. So we have radio telescopes, these things that you might have seen, and then there are optical telescopes, of course, and then there are like IR telescopes. So the recent JWST, if you have heard it, that is one of those IR telescopes, infrared telescopes. And these might be on Earth, these might be in space. So this is an image of like an observatory that is called Keck Observatory in Mauna Kea, and these are kind of optical telescopes. One is Subaru telescope. And Gaia, that's now coming on to the main topic. So Gaia is one of these telescopes, or satellites you can say, that is in space, and it is not looking at the Earth, it is looking up at this space again. And it was launched by ESA, that is European Space Agency, and it collects some bunch of data. What its primary goal is to look at around 1 billion stars in our galaxy, stars and even other objects like comets and stuff, but mainly stars, and get three types of data. So first is the photometric data, that is like to measure the luminosity or how bright a star is. The second is spectroscopic data, that is to say how bright a star is in different wavelengths. And then the third is astrometric data. So that is the positional and the velocity data of stars. So this on the left is Gaia, and as you can see, it is in the space. There is sun, then there is Earth, and then there is Gaia. Okay. So on the right you can see, for any two-body system, here sun and Earth, there are 5 points of gravitational attraction, where the gravitational attraction due to one body cancels out the attraction due to the other body. So these are basically points that are very stable for orbits. and Gaia is placed on this L2 orbit, that is the Lagrange points. These are called Lagrange points, and L2 is where Gaia is placed at, so that it can look at the stars. And so first point I have already covered. The second point is that it has two type of cameras or two type of telescopes that are positioned like 106 something degrees apart. And these two cameras, both of these are like gigapixel cameras, so these have 10 to the power 9 pixels, so you can already imagine how big the data would be. And this has an astrometric accuracy, that means it can look at stars as small as a few micro arc seconds, which is to say, if we place an orange on or a donut on moon and we try to see it from Earth, so that's how precise it is. So you can imagine how small things it is like looking at. And this is a GIF showing how these two cameras are aligned. So we have two cameras just to ensure that we have a wider field of view, also that we have absolute astrometry as compared to like just one point compare against other. Moving on, so we have Gaia data, that is the data that is downlinked by this satellite to Earth, and there are these 6 things that I'll be talking about. So let me just quickly move on. I'll try to wrap things quickly. So first is this right ascension and declination, which is just to say that this is kind of the coordinates in the sky which are not present in the Earth. So on the bottom here you can see like we have an equator and stuff like that on Earth, but we also have an orbital plane. Earth is a bit tilted, so we have this celestial equator and we have a right ascension. So let's say that this is 0 0 coordinate, and if we were to look at a star called Aldebaran or any star, we have a right ascension. In the kind of terms you can say it like longitude, and then latitude is declination. So this is just simple terms to say these are coordinates of the stars. Then we have parallax. So if you like try to look at your finger with one eye closed and then the other eye closed, you can see like there is an apparent shift of position of our finger. That is parallax. We use this to calculate distance. This is how our vision works because we have two eyes, right? So what we do is on the bottom you can see like in the middle there is sun and the Earth is orbiting around it. So at one point we look at the star that we want to measure the distance at, and then after 6 months we look at the same sky and we calculate that angle, that is a parallax angle. Since this angle would be very small, since it's very far away, so we can just approximate sine of this angle as that angle itself, and we can get the distance like 1 by this angle, just p by s, simple trigonometry. So moving on, this is the second type of data we have, distances, coordinates. The third type is radial velocity. So have you ever heard an ambulance or any car approaching you? You'll see like this thing. As it grows closer to you, the wavelength compresses. As it goes farther away, the wavelength just stretches. And when the wavelength stretches, stars look red to us as they are going away. When they are coming towards us, they look blue. So this is called radial velocity. It is the velocity in our line of sight. And then we have another type of velocity, that is proper motions. So this is the transverse velocity. All of you might be aware of this. This is the Big Dipper constellation. But on here you can see there is this time that is being changing, and it shows that these stars are changing their positions ever so slightly. So dinosaurs probably did not see the constellations the way we did. And they also saw different stars because they were on the other part of our galaxy that time. So this is called the proper motions, and in RA index, so basically proper motion in latitude and longitude. So we call them proper motion in RA, proper motion in DEC. And the resultant is the transverse velocity. Moving on. So now we are coming on to the main topic, that is Gaia data releases. So Gaia automatically, so it makes its data that it collects openly available to public, and there are also more telescopes that does this. So you can also access this, and we have like around 2 full data releases right now, DR2. So Gaia Archive is a site that hosts this data that we can query our stuff on. So we do not need to get all the data in our system before querying it. So we will use this Gaia Archive, which can be found at this link. If you have opened this whole slides, you can see it. But let's see here. So this is the Gaia Archive, and you can just basically search for data over here. So let's just do this, and we'll be searching first 2000 stars in 3 arc minutes. So arc minutes is just like a smaller version of degree. So one degree has 60 arc minutes, 1 arc minute has 60 arc seconds. So we'll be looking at 3 arc minute radius in the sky, and we'll be getting 2000 stars around a globular cluster, which is a star cluster called Messier 5. And then we'll be reading this and plotting this in Python. Okay. So first of all, we'll be searching this name and then putting 3 arc minutes into this archive. So I'll put here Messier 5, and it should resolve it. So it says that Messier 5 is resolved by this particular database, and on the radius end we said that we'll be needing 3 arc minutes. So I can just select arc minutes from here, and since we are using the DR2 data release 2, I'll just be putting Gaia DR2. Alright, so once I do this, we can also have some extra conditions which are SQL where conditions, and we can also display columns, like what columns we want. For now we'll just be using array and deck so that we can plot these stars. So if I just submit query, it will give me a table of these stars, and I can download. It will take a bit of time. Okay, here it is. So this is the data that we had, and we can download it as CSV file so that it is easier for us to load in Python. So I have already done this, and it is present on the repository or the binder link if you are using that. So I'll just go ahead and show you that. So I guess this would be too small. Let me know, is this fine? Can you read this?
Yeah.
Alright, so first of all, I'm importing the libraries, NumPy, Pandas, Matplotlib, and then I'm just reading the CSV using Pandas, and just this is the rows that we had. So this is our data. We want array and declination so that we get the coordinates. Moving on ahead, as I'm trying to plot this, I'm just making a scatter plot of the array and declination, and here you can see we have all these stars in Messier 5 3 arc minute radius. So this is something that you can do with this data. Okay. Isn't this fascinating? It is fascinating to me. I left my job for this. So anyway, we can also. Messier 5 is a globular cluster. That means it is a cluster of stars that were born together, almost at the same time. So there are a lot of stars in that cluster. That's it. Yep, the stars are continuously moving, but at a very huge time scale. So those motions, we capture those motions. We can also plot those motions. So that are proper motion array and proper motion deck that are also available in this data. And we also have parallaxes, so we can also plot those. But these are like you can do this yourself. And then querying with ADQL. So ADQL is just like SQL, but it has some additional functions. So additional functions means it has geometric functions. As we saw, we are looking at 3 arc minute radius in the in the sky. That is done by geometric functions in ADQL. We won't be using this. So I'm just skipping this since all of you at least know a bit about SQL. But our basic query structure is select in a table form data, select some columns from that table name where some conditions are met, and we can order by columns. So if I were to select 100 stars closest to Earth, I can do this simply by saying select top 100 stars. These are the column names. I'll need array, declination, parallax, some errors, and a source ID so that I can identify them separately. From this table Gaia source, where parallax is greater than 0, because we saw there were some NaN values, not a number values. We do not have parallax for all the stars yet in this release. And then order by this parallax by descending. Since parallax angle was 1 by distance, I am just ordering it by descending parallaxes. That means I'll get largest parallaxes or the smallest distances from the Earth. So I can get top 100 stars over here. And let's do a small project. You can also try this in the notebook. So I'll be getting 10,000 closest stars with these parameters. You can just see this in the notebook itself. But basically what we are doing is we are getting the colors of the stars, how they would be visible to human eye. Then absolute G-band photometric magnitude. This just means the brightness of the stars. The distance we can calculate using parallaxes, array and declination, these are the coordinates, radius and effective temperature. and let's see what we can plot with this. So I have just put in some hints. So distance, the parallax is in milliarcseconds, so you'll need 1000. PPRP tells us the color, absolute photometric band tells us the brightness, and this is the formula that we can calculate absolute photometric brightness from, and that's probably it. So this would be the query. Select top 10,000, the formula for absolute G band magnitude, the color, the distance, RA depth, radius value, and effective temperature. Where from this table, where parallax is greater than 0 again, and order by parallax, since we are getting the closest 10,000 stars. So I am trying to plot this, and this is just a simple plot, plotting the absolute magnitude and the colors. So, and I'm reversing this because the magnitudes in astronomy are in opposite order. So 25 means it is like fainter, while 5 means it's brighter. So it's opposite. So this is called a color magnitude diagram, and we had some more data. So let's go ahead one step and do something like this. So I'm still plotting the same things. The size is now radius value of the stars. The color is given by the effective temperature, since that is how we see stars, and the color map is red, yellow, blue, and the same thing. So this is called a Herschel-Sprintz HR diagram basically. This again is telling us the brightness of the stars and GPRP. So you can see this is a standard thing that is printed on top of most of astronomy books, that are to say there are some red dwarfs, these are the red giant branch, and these are the blue stars. Our sun is somewhere around here, because this is the yellowest spot in here. Our sun is somewhere around here. So you can see these are the type of stars that are present in all the universe, and we can classify all the stars that are present in universe around this diagram. So this is a pretty famous diagram as well. And we can also make a 3D plot. So I'm just doing the same thing, just plotting it scatter 3D using matplotlib, and I'm also now using distances. So this is not interactive in the slide, but you can try this on your own in the notebook. It would be interactive, so you can zoom in and check it, go into the stars and so on. And GaiaCurves, this is a small open source package that I made. So you can also do stuff like getting light curves of these stars, which is to say that you are talking about how stars were moving, right? Stars are also variable, so they are emitting more light at some times than others, and in different wavelengths. So this is one open source package that I developed, a very small package that can do this. So what it does is you can just give a star name, let's say NQDRA, which is a variable star. We know that it varies its brightness, and I'm just fetching this curve and putting it into an output directory, so it saves this, and then you can see this star is varying in brightness for all these different bands. G is the green brightness, so if we were to see the star in green color, it would be varying like this and so on. So you can also analyze how stars are varying by time. So this is just a small thing. You have other archives, such as for my research work I use TESS. TESS is another satellite that looks at planets, other planets, not in our solar system, but planets hosted by stars other than our sun. So what I do is I try to find those, and that is also openly hosted. So all the data that I have been using is openly hosted, since this is taxpayers' money, even in India. So they are entitled to this data, and you can also try this. This is cool work, and there are citizen science projects which you can contribute to. So they just ask you to do simple things like, can you see a bright dip in the brightness of the star? And if you do indeed see a good dip in the brightness and you find a planet, by looking at those dips, you'll be getting your name on a paper, or you will be getting an acknowledgement on a paper. So that is one great way to also build your portfolio, that you have also tried this thing. And these are all open source tools. Since the data is open, everything is also open. The field is not like money making field, it is open source field. So I urge you all to check out these citizen science projects. You can just type in Astronomy's citizen science projects, and you can contribute to this. That would be all. Thank you for listening.